Hey, this is Mr. Ariel. I'm here today with another part of the notes for atomic bonding. So far, we've learned about the three types of bonds that atoms can make. They're ionic bonds, covalent bonds, and metallic bonds. What we need to pick up today is some more information about each type of bond, specifically the properties that come along with each type of bond. Let's go ahead and get started. Alright, now the first idea to get in your notes is the difference between a molecule and a compound. Molecules are any substance joined together with covalent bonds. Remember, that's two or more nonmetals joined together. Something like carbon dioxide, CO2, that's two different nonmetals, carbon and oxygen, so we know it's held together by covalent bonds. So every single molecule of carbon dioxide is a carbon atom joined to two oxygen atoms. Here's the Lewis structure, but here's what a picture of carbon dioxide, the molecule, would look like if you could see it close up. The point of this is, when you look at the chemical formula for a molecule, it tells you the exact number of each type of atom in the molecule. Like if I had two molecules of CO2, each one has two atoms of oxygen and one atom of carbon, but the molecules are separate from each other. Now you might be saying to yourself, that seems kind of easy. I think I could have figured that out on my own, and you're probably correct. Things get a little bit different when you look at compounds. Now, compounds are what we call substances that are held together by ionic bonds. Remember, that's going to be a metal cation and a nonmetal anion joined together. So something like sodium chloride, NaCl, that's ionic because it's made of a metal, sodium, joined together with a nonmetal, chlorine. Now, for what the chemical formula of an ionic compound tells you, it's not the same as what it did for covalent. For covalent substances, the chemical formula tells you the exact number of each atom in the molecule. For ionic compounds, the chemical formula tells you something different. It tells you the formula unit for the compound. And a formula unit is the smallest whole number ratio of the ions in the compound. So for my example, NaCl, the formula just tells us that there's one sodium for every one chlorine. But it doesn't mean that sodium chloride is just a single sodium and a single chlorine. In reality, sodium chloride exists in cubes. You've probably seen them in table salt. It should be kind of familiar. Here's a drawing of one, and each of these are the ions. These green ones are the chlorine with a minus, and then the purple ones are sodium that's positive. Overall, these two ions stack together in this pattern so that each negative ion is surrounded by a positive ion on all sides, then each positive ion is surrounded by a negative ion on all sides. The point is, the chemical formula of an ionic compound doesn't tell you how many ions there are. I mean, there's no such thing as an ionic molecule. Instead, the formula just tells us the formula unit, and that's the ratio of the atoms in the compound, like this one is one sodium for every one chlorine. In a single grain of table salt, there would be trillions of individual ions that make it up. Now make sure you've got all of this information in your notes because I need to move on. Now on this next slide, we need to figure out some properties that come along with each type of bond. Go ahead and set yourself up a table in your notes. Here are the labels you'll need for the first row and the columns. Pause the video to draw it into your notes and then come back and we'll fill it in. Now you need to know that ionic bonds are much stronger than covalent bonds, so add that to the top of your notes. The forces required to pull apart two ions from each other are much greater than the forces required to pull apart two atoms in a covalent substance. Now for phase at room temperature, phase means is it a solid, a liquid, or a gas? Well, ionic substances are always going to be solids at room temperature because to overcome the forces holding those ions together and let them kind of slide around as a liquid, that would require so much energy that it's just not possible at room temperature. Now we can go ahead and jump down to the melting and the boiling points. If they're solids at room temperature and it requires so much energy to break apart those ions from each other to cause them to be a liquid and then a gas, that means the melting point is going to be extremely high. Like for example, sodium chloride has a melting point of 801 degrees C. I mean, water boils at 100 degrees Celsius. In Fahrenheit, this is 1,474 degrees Fahrenheit. It's really hot, just to melt sodium chloride. So let's go ahead and fill in the other boxes for ionic substances. For the crushable box, I couldn't think of another word for it. Ionic substances are extremely hard. They're not crushable at all with normal amounts of force. For the conducts electricity box, Ionic things do conduct electricity, but they have to be melted or dissolved. Electricity involves the movement of charged particles, and so if these charged particles are free to move around, when they're melted or dissolved in water, then the substance will conduct electricity. If it's like a solid cube of table salt, that can't conduct electricity at all. Two more things we need for ionic bonds are their odor and smell, or if they're soluble in water. Well, odor and smell is pretty easy. If these particles are so tightly held together by these really strong ionic bonds, that means none of the particles in the substance will be able to break loose from the substance. And so ionic substances usually have no odor at all, because none of those particles can reach your nose. Now, last up for ionic bonds, are they soluble in water? Yes. Things that are ionic typically will dissolve in water extremely well. If you remember from a previous set of notes, that water has a structure that looks like this, and it has little positives, partial positives, and it has partially negative oxygen. So something like sodium chloride can break apart into ions, and those chlorines that are negative, well, they'll be attracted to the hydrogens, and then the sodiums will all be attracted to the oxygens, and that'll cause it to break apart and dissolve. Now, moving on with covalent bonds, remember those are held together by weaker bonds. So for the phase at room temperature, well, they can be solid, liquid, or gas. It just depends a little bit more on the molecules themselves. For the crushable box, ionic things were very hard and not crushable, but covalent bonds tend to be softer than ionic substances. You can often crush them between your fingers. For melting and boiling points, covalent things have a lower boiling point and melting point compared to ionic substances. For conducting electricity, covalent substances don't, because when they dissolve, like say we have a glass full of water and we dissolve some sugar, well, that sugar just breaks apart into individual sugar molecules. I mean, it was a big grain of sugar, and that simply breaks apart into individual molecules of sugar. But none of those molecules have any charged sections on them, and so electricity can't move through this substance. For odor and smell, remember these bonds are weaker than ionic bonds, and so covalent substances often do have an odor, because parts of the molecules can break off and reach your nose. And then for the last category, soluble in water, that gets us sometimes, because sometimes they are soluble and sometimes they're not. Now make sure you've got all these ideas in your notes, because I need to move on a little bit. Now we need to finish up the notes today by figuring out a few things about metallic bonds and the properties that result from them. First up, metals are good conductors of electricity. Just like before, for electricity to move through a substance, it has to have charged particles that can move. So if this picture down here was a section of a metal wire, and you applied an electrical current to one end, that would cause each of the charged particles to move around and bump into the next one, and to the next, and to the next, and that electric current could keep flowing. The point is, these charges have to be able to move, and they can in metals because we have those delocalized electrons, or the sea of electrons. So metals are good conductors of electricity. Next up, metals are quite malleable. That means they can be hammered or rolled into thin sheets. Aluminum foil is a great example. If you think of a chunk of aluminum, kind of like it's a batch of cookie dough, you can end up taking that chunk and causing it to be rolled into a very, very thin sheet. It requires a ton of pressure to do this, but industrial machines are quite capable of rolling out that aluminum into a very, very thin sheet. The next property is ductile. Metals tend to be ductile, which means they can be pulled or pressed to make wire. You can kind of think of ductility kind of like it's chewing gum. And if you were to grip each end and pull it apart, it won't break. It'll just get thinner and thinner in the middle. And eventually you'll end up with a long, skinny piece, and that's a wire. Now, both of these properties, malleable and ductile, are because of these delocalized electrons. If you were to apply pressure and push on these molecules down below, they can just slide past each other because of those delocalized electrons will allow all of the ions to flow around each other without breaking. Now, if you were to do this with an ionic compound and you applied a little bit of pressure to the bottom section of it, as soon as you shifted it so that two negatives line up with each other and two positives line up with each other because they're rigidly held in place, the whole substance will simply break. So ionic compounds are really brittle, but the opposite of that for metals is they're malleable and ductile. Now, the last property of metallic bonds we need to get today is luster. It's how shiny a substance is. And metals tend to have a very high luster. In other words, they're really shiny. Sometimes metals aren't shiny on their own, but you can polish them or grind them down to make them shiny, and that's not something you can do with ionic or covalent substances. Now, if you've got all these ideas into your notes, you're done with the notes for this lesson. I hope the video has been helpful to you today, and as always, thanks for watching.